All right, hey folks, welcome back. We've been talking about neutralization reactions, and we first looked at hydroxide bases. Now we're going to look at carbonate and bicarbonate bases. Okay, so what are carbonate and hydrogen, or also known as bicarbonate bases? Well, these are ionic compounds that contain either hydrogen carbonate, also known as bicarbonate, which is HCO3 minus, or carbonate ions, which is just the CO3 minus 2. Any ionic compound with these anions are weak bases. They're frequently used in neutralization reactions. They can react with acids to produce water, an ionic compound, and CO2 gas. The most famous or well known to students example of this is baking soda and vinegar, right? Like the old elementary school volcano that you could make. The reason it does that is because it produces CO2 gas, which bubbles through the solution. So it's vinegar, which is basically acetic acid, and sodium bicarbonate, which is sodium ion with HCO3 minus. It produces water, a salt, just like before, but it also produces CO2 gas. So this is a fun one, and it's easy to do. If we want to simplify it, just trying to look at this reaction. The acetic acid is kind of complicated, but we'll just call it A, right? All this, so like the acetate part, just call it A. Then we can see this a little more clearly. Okay, and so we should see how it balances out quite nicely. And also notice the difference between this and the previous one, HCO3. If I rewrite it, kind of to compare it to like an OH, right? We see this, the difference is just a CO2, right? And that's what shows up here. So this is just like hydroxide ones, except we also get a CO2. We get carbon dioxide gas, and that's because of the carbonate. Right? Okay, let's just jump right to the net reactions. And now it's hopefully really clear what's going on. So if we have a hydrogen carbonate, HCO3 minus, and any acid, and all we really care about the acid is just the H plus, right? We'll end up with water and CO2. Now there would also be a salt, right? Some ionic compound, but that's not a part of the net, that's spectator. If we have carbonate, which is just CO3 minus 2, it's going to take 2 H plus, and we still get water and carbon dioxide. And it takes 2 hydrogen, maybe that makes sense, right? Because there's already, we're missing one here. Basically, we need 2 to make water and get an oxygen off of the carbonate to get water and CO2. The nice thing, though, is look at the products. They're the same, whether you have carbonate or bicarbonate. The balancing comes out to be a little different, but the products are the same. And again, they're neutral. Okay, so here's practice exercise 933. Write the complete balanced equation for the reaction between hydroiodic acid, HI, and potassium hydrogen carbonate, KHCO3. What are the spectator ions? What is the net reaction? So there's actually 3 questions here. First, we're supposed to write a balanced equation. So let's do that. So we have HI plus potassium hydrogen carbonate. And without really needing to balance anything yet, we know what we get, right? We get water and CO2. So we get H2O plus CO2 gas. And in this case, we'll have a salt as well. We get Ki dissolved in water. That's the spectator ions. I guess that kind of gives away the next question, doesn't it? But anyway, is this balanced? What do you think? Yes, indeed, it is balanced. Everything works out quite nicely, right? When we have one proton and one bicarbonate, then we get a nice balanced equation without having to add any coefficients. So then part two is what are the spectator ions, which I already kind of said and gave away, but it's K and I, right? The I and the K are still just I and K as ions, so those are the spectators, which means if we remove those, we get the net reaction, and so that would give us what? Just simply the neutralization H plus HCO3 minus makes water and CO2. All right, so I mean that's kind of the extent of where we're going with this, and just make sure everything is balanced and you're good to go. All right, here's a question. Should be pretty simple now. What are the products of the reaction of HCl and NaHCO3? Answer for yourselves. Okay, well, it's a neutralization involving bicarbonate, so it's always going to produce water and CO2, right? And a neutral salt. So that would be water, CO2, and NaCl. Okay, so the last question was about bicarbonate. And if we have carbonate, it's slightly different, but not really. Just kind of a matter of balancing. So I'm going to give ourselves a question like this with a little more context. This table shows the active ingredient in common over-the-counter antacids. So you might recognize many of these names. If you look, the first three rows are hydroxide bases, right? Basically, one is aluminum hydroxide, and then we have magnesium hydroxide, and Malox and Mylanta are a combination of aluminum hydroxide and magnesium hydroxide, and then Tums and Rolaids are calcium carbonate. Calcium carbonate, also like chalk, right, or something. But how do Tums and Rolaids react? How do they work? How do they neutralize the gastric juices? How are they antacids? So here's the reaction, right? So we have HCl plus CO2. Sorry, HCl plus CaCO3. And what happens? Well, we know that we're going to get water and CO2, and then what's left over? And we're going to have to balance as well, right? We get a salt, calcium chloride. And two things might jump out right away, H2 here and the Cl2 there, but we don't have two H's or Cl's here, so we're going to need to put a 2 in front of the HCl, and now things shall be balanced, right? If we remember back to the net, we said 2H plus in carbonate, so now we get it. This would be a spectator, right? It's just a salt that would result, but we do have the reaction. 2HCl plus calcium carbonate makes water plus CO2 plus calcium chloride. So that's the reaction going on when we neutralize or try to reduce some gastric juices. Obviously, this is not neutralizing the entire stomach. We don't have equal amounts. You don't want to take too much of this. Also, it produces CO2 gas. But that's the equation, and that's how it works. So to relate this back to some past experience, I have an additional question that I would like to ask. So here's that net ionic equation. How many moles of H plus ions are neutralized if you take 2 tablets of regular strength Tums? And regular strength Tums, say 500 milligrams of calcium carbonate each. Okay, so we're going to take 2 tablets, and we want to know how many moles of H plus ions. And we have a balanced equation. Great. We've done this kind of question before. We've never done this particular question, but let's think through it here. All right, so we're going to start with our known quantity, right, which is the amount of calcium carbonate that we consume. So it's mass of calcium carbonate. And then we want to convert that to, probably want to get out of mass, right? We eventually want to get to moles. The ratios of things here are mole ratios. So we're going to want to convert from mass of calcium carbonate into moles of calcium carbonate. Our balanced equation does not actually contain calcium carbonate. It contains carbonate. We could do a conversion to moles of carbonate, and then from there we can get moles of H plus. And every arrow is a conversion factor. You know what, I'm actually going to start. Let's start at tablets. Okay, let's start there. So that's the known quantity. 2 tablets. And then we will convert into mass. So there's 1/2 gram of calcium carbonate for every tablet. See if I can color code my canceling out here. Okay, and then we want to go from calcium carbonate grams to calcium carbonate moles. And to do so, we need what? We need the molar mass, right? That connects between grams and moles. And you can find this, look at the periodic table, take the atomic mass of calcium, take the atomic mass of carbon, and add them together, and then add the atomic mass of oxygen times 3, and add that. And if you're really good at that, you can just simply look it up, to be honest. So if either one, you calculate it yourself, or we'll look it up, it is 100.1 grams of calcium carbonate. Whoops. It is 100.1, but I did that in the wrong place. What was wrong there? We want to convert into moles, right? So moles should be on top. And then I have 100.1 grams of calcium carbonate. Okay? Now, we want to convert, we really want moles of carbonate. And this is an easy step, but I'm going to include it just to be complete, that for every 1 mole of calcium carbonate, there is 1 mole of carbonate, right? So numerically, this step does nothing. It's just simply part of converting the units. Okay, and then we have one final step. For every 1 mole of carbonate, we have 2 moles of H plus. All right, and I tried to color code things here. So right, tablets cancels out. Grams of calcium carbonate cancels out. Moles of calcium carbonate cancels out. And moles of carbonate cancels out. And what doesn't, what's left over is moles of H plus, which is what we want. So if we were to look at just numerically, right, we have 2 tablets times 0.500 times 2 divided by 100.1, and the units will be moles of H plus. You may even notice that dividing or multiplying by 1/2 and multiplying by 2 cancel out, but that's fine. So anyway, final answer is 0.02 moles of H plus. One remaining question. What is, or how many ions is this actually? Right, and what does that mean? So 0.02 moles of H plus is how many ions? Well, now the definition of a mole is what? That means we have 6.022 times 10 to the 23 ions per mole. That's the definition of a mole, is things, like how many, like 6.002 things per mole is the unit. So take our 0.02, multiply by 6.022 times 10 to the 23, and 2 tablets of regular strength Tums neutralizes 1.20 times 10 to the 22 H plus ions. That's a good bit of review there, right? So that may sound like a lot, but you have much more than that in there. So okay, this wraps up section 9.3 about neutralization reactions, and a little bit of review here at the end. So we have one section remaining, which is about buffers, and I'll see you then.